All right, everybody, hello and welcome back to another very exciting topic, generalization and decision making. So here we are talking about conceptually making generalizations and decisions using research. We have another part to this, our types of analysis lectures, which should be taken together with this, right? You should have already watched it. You shouldn't be thinking about one without the other, really. So this is the conceptual overview of generalization and decision making in research. It's looking under the hood of generalization and decision making in terms of the statistics that we use. But here we're just talking conceptually. How do we make decisions in science and specifically in psychology? So we have this idea here that we will talk about first, universalism. This is the assumption that a finding will apply to all people. Take some relatively famous psychological findings. We can take something like the Zimbardo prison experiment, the Stanford prison experiment. The idea behind a study like that, individuals, young men, college-aged men, were randomly assigned to play the role of a prisoner or a guard in a simulated prison. What happens is very quickly the guards took on the role of guards in a very serious way, including some harm to the prisoners. But the idea is that a generalization was made from this experiment. The generalization being, if we put people in positions of power, they're going to act a certain way. That, of course, is an unethical experiment that we can't necessarily recreate today. But the idea of psychological research in this way persists, that we want to be able to apply phenomena from a small group of people to others. And this is imperfect. Universalism says that the principles of psychology will not vary, but we know that it can. We know that psychology is not completely consistent across all individuals, all cultures, all time periods. Universalism is that psychological findings will apply anywhere and will be the same for all people, irrespective of society and culture. Do you think this is true? I would say, I don't think so. We might be able to think of some instances where it is true and certainly some where it's not true. If you look at collectivistic versus individualistic cultures, this is a comparison of the two. So this is a social psychology or sociology idea that we have cultures that are inherently different on a set of characteristics. In a collectivistic society, groups are treated as greater than the whole. The self is viewed as part of a group. We see other trends, a slower pace of life, lower heart attack rates, lower divorce rates, indirect communication. Also some abuses that happen. In individualistic societies, people view themselves more as individuals. The self is viewed as independent from other groups, faster pace of life, higher heart attack rates, so on. So we know that universalism can't be applied as a blanket to everybody because we see these cultural divides that are pretty clear here, okay? So the cockroach study, you might be thinking, why are we talking about universalism if it's so flawed? Well, because it works in the other direction too. Sometimes we can take behavior from something even inhuman. Psychology is the study of the mind and behavior, and we can do that in animals as well. And here's an example, one of my personal favorite studies. This is using cockroaches. So we have a test box or race box or maze box. These are used often in comparative animal behavior. We compare animal behavior to human behavior to see if we can get to the bottom of any trends in behavior. So we have cockroaches completing a simple maze. And the goal is scientists are measuring how quickly a roach will get from one end to the other of this maze. The experimental condition is that they'll have the cockroach go through the maze by itself, and then they'll have the cockroach go through the maze with an audience. And one of my favorite terms I've ever seen in a scientific paper is cockroach audience boxes. So what happened was the cockroach went faster and performed better when it was put in front of a cockroach audience. And this might seem absurd. What do we care about this? What we care about is that if we put humans in the same scenario, humans performing a simple task in front of other humans, we see an increase in performance as well. And this is just one example of how behavior somewhere else can be applied or generalized to human behavior, even from animals as strange as cockroaches. So that's the idea of generalization. When we do statistics, when we come up with a finding, we want to know who else that finding applies to. In some cases, the scope will be very small. In other cases, the scope will be very large. And that often has to do with sampling, how we sample or who is included in a particular study. So a sample is a subset of people, a group of people that you use to conduct a study. Sampling can be done in a number of ways. We can sample randomly, non-randomly, but who we sample is going to have an effect on our decision making and on our results. So I have a little term here. Psychology is the psychology of psychology students. So this is interesting. Psychology research started on psychology students, and it mostly continues on psychology students. So the general idea is, are our samples representative of the entire population? Can we make generalizations to the entire population if we're only looking at this certain slice in our sample? So when we take a sample, we expect to be able to make some inferences from that sample back to the population. We're assuming that there's some similarity from our sample that can be moved back over to everybody else. So where this is an issue is sometimes samples are not representative of the population. Sort of like politics. We have representatives who are meant to represent a group of people, and we all know how well that works, right? It's not without error for sure, but the idea is the same. We want groups of people that represent the entire population. Then we have something called a convenience sample. Okay, very different, where we just grab whoever is closest and who's available, which is basically what you guys are going to be doing. Okay. So generally larger samples are regarded as better. By better, we really mean it's more representative. So if you think of an entire population, the more people we take from that population, the more representation we have from that population. It's just a law of numbers. The smaller your sample, the smaller your sample, the more people you're missing. But this is sort of a double-edged sword. So a larger sample that's not representative might yield significant results, but they might not be entirely accurate or generalizable to the whole population. Okay, this is a probability issue. Probability can be manipulated relatively easily. It's still just a chance that something happens, and with a larger sample, we're more likely to get that chance of something happening. Another concern we have when sampling is weird populations. So this is a newly coined term. It's actually a term that captures the issues we have in general sampling. WEIRD is an acronym for who is most likely to participate in a research study. So W is white or Western societies, lots of research being done here. So of course we have more people who are Western. Educated, you're going to participate in some research this semester. You're getting educated at, we do research mostly at universities. I is industrialized. Industrialized countries have more access to research and research resources. R is rich. Research requires money. Richer countries are more likely to be putting funds into research. D is democratic. Democratic countries are more likely to have research programs because we're more likely to question things than like a communist country. So this is an issue for a number of reasons. We can only do research on those we have access to, and we need consent. So the people most willing to participate are people who understand the importance of research. Those surrounded by research in their professional life, usually more educated people. So a personal example, I worked on a study at UCSD looking at attachment in children. We wanted to compare securely attached, avoidantly attached, anxiously attached infants. So we did outreach in the community, and the bulk of our participants were people who worked at the college and had kids. We were working with a very weird population. We didn't have a lot of children that were anxiously or avoidantly attached. We were talking about families who were financially stable, where connection, caring for children was maybe easier than in other groups. So we need to know who our samples are. When we read a paper, we need to look at their method and determine who they included to see if their results should be generalized to greater groups of people or not. Hypothesis testing. Okay, so let's do some hypothesis testing review. We're talking about predictions. You've made a prediction in this class, or you're going to. Our predictions often have a direction. So, for example, let's say you have found a new chemical. I talked about this in our introduction. A chemical that helps people sleep better, but you're afraid it might disrupt the sleep pattern. So, basically, you're going to see how is this affecting people's sleep. It's going to help improve sleep or reduce sleep. But it's going to affect sleep no matter what, right? So we've got that two-tailed hypothesis, okay? If you were working with something that had already been shown to increase sleep, your prediction would probably be a one-tailed hypothesis, okay? You're only looking at one direction versus two, okay? So moving on to the whiteboard. So here I have a normal curve. When we're talking about data, we often assume it's going to be normal, that most of the data will fall in the center while very little data will fall out into the tail. So let's take the height of individuals. Let's say the average person is 5 feet 7 inches tall. You might think of where you fall in this distribution yourself. Okay, so I fall over here on the negative end because I'm short, but there are people over here on the positive end as well. So we've spread around the mean, standard deviations, how far do scores deviate from the mean. So taking height as an example, maybe some people are 5'9", some are 6'1", my husband's 6'4", maybe 3 standard deviations away, we're approaching the 6'3" mark. So he would be, considered pretty tall, maybe even abnormally tall. He's, many standard deviations away. So normal and abnormal in statistics means something very different than in our normal language. Abnormal means it's not near the rest of the scores. It doesn't mean it's bad, it just means it's abnormal. I love that he's 6'4". So when we do a hypothesis test, we're looking at a population that's normally distributed. If we get a sample and compare them to this population, where do they fall? Do they fall close to the population, or do they fall over in that abnormal area? So we can think of these normal distributions using probability. Most people fall in the middle, very few fall in the tails. We determine a certain percentage as abnormal, usually 5%. So alpha equals 5% or 0.05. So if we're looking in the tails for abnormality, we're only looking at 5% of most extreme scores. If we want to detect the difference between groups, we need to see one group close to the population and one over here. This would be a significant difference, okay? So what is a p-value? Again, a p-value is probability. Our hypothesis testing is based on probability, the unlikeliness that something is going to happen, or something is, were to happen. So the bigger the effect or association that's expected, the smaller the sample can be. A statistically significant finding is one that's large enough that it's unlikely to be caused by chance,
alternative hypothesis.
Fluctuations.
So we can have a null hypothesis that says
there's
no difference.
Let's come up with a hypothesis.
And we can have an alternative hypothesis. That's our prediction. So let's say that we are predicting, let's say that we think that younger people, and we'll stick with the college population. So let's say maybe for younger group, we'll say less than 25 years old. So younger people spend more time on screens. Okay, that's our hypothesis. And we'll go ahead and think about this on a normal curve here. The null hypothesis would be that there's no difference, right? Here for comparing younger people and older people, the null would be that there is no difference between the groups. So let's say that we have a normal curve. We're expecting this data to be normally distributed. That's an assumption that's often made when we're doing statistics. We assume normality of our distribution. So let's say that we have some population value. We're assuming normality, and we know that the average person, or the average person across all ages, the younger people population, or the younger people sample that we'll take, is what we want to compare to the general population. So if you remember these terms, we have a sample mean. X bar is the sample mean. Mu is the population mean. All right, so let's say that for the population, we know that the average person spends, let's say 4 hours on screens a day. All right, 4 hours. So our average here, the center of this distribution, will be something like 4 hours. And let's say that there's a standard deviation, right, sigma. Here's a little standard deviation. Let's say there's a standard deviation of 1 in the general population. So remember, even if you're not familiar, don't recall what standard deviation is, it's just how far we stray from the mean. So if 4 hours is the mean, if we go up in 1 hour units, we would have 5, 6, 7 hours. If we go this way, 3, 2, 1 hours. So in this population, anybody over here, kind of over in this tail, might be considered abnormal. Anybody over here might be considered abnormal as well. In its current day and age, in this current day and age. So let's say that we grab a sample, right? We grab a sample of younger people, and the younger people, let's say that they're getting 9 hours of screen time a day. Which, again, if people are like doing telework or whatever, that might not be unreasonable of a number. Right, so let's say that we get, if we plot that onto this distribution, remember what we discussed, most people are going to be here. Most people are going to be in here, statistically, right? We're going to see most people in the center. So if we get something like 9, we plot this. This is way over here. This makes it seem like younger people do spend more time on screens than the general population. And how we would actually determine this is we look at the percentage of how likely it was that we got a score over here, if this is true of the entire population. Using some general math here, we know that about 99% of scores are here. And we'll talk a bit more about this when we talk about the normal curve. So the likelihood of this happening was very little, very small, less than 1% in this particular example. So just an idea of how some of these topics sort of work together. We're looking for abnormality. We're looking for cases where our sample seems very different than one that was already known about a given topic. So the larger a sample that we have, the more likely we are to detect an effect. The larger an effect is, the easier it is to detect in a smaller sample. So the more individuals we have in a sample, the more likely we are to see significant results just due to probability, just due to having more data. The larger the effect or association, the smaller sample we can have to observe it effectively. So even with small samples, we'll be able to observe differences that are strong ones that we would expect to be present. Okay. So all of this is about statistical significance. If you find something significantly different than what was already known or the null hypothesis, you have a significant result. This is what scientists are often digging for, finding something previously unknown about the population. To make this more conservative, we can push our p-value over, make it harder to successfully reject a null hypothesis. If you have a distribution of data, 100% of the data is here somewhere. If you're using an alpha level of 0.05 in a one-tailed test, 5% of the data is over here. These are extreme or abnormal scores. But what if we're testing something as serious as a drug that has a side effect of death? When we give somebody a pill with a side effect as serious as death, maybe we don't want there to be a 5% chance that they fall into that group. We can make our testing more conservative. Instead of 5%, we can change it to 1%. We can test so stringently that there's only a 1% chance of seeing the side effect. So an alpha level or significance level is just a probability, the likelihood that something might happen. So how do sampling and statistics work together? Larger samples drive statistical significance. We can fight this using something called effect size. Many of our statistics use in sample size, which is sample size, right? So sample size can influence significant outcomes. Effect size looks at something different, the pure magnitude of difference between whatever you're comparing. Effect size uses means and standard deviation in its calculation, but it looks at the magnitude of difference. Measures of effect can be helpful in cases where we might have a correlation that comes out insignificant because there's no linear relationship. So back to the whiteboard, we can have strong positive correlations that go upward, strong negative correlations that go downward. We use R values, maybe 0.9, maybe 0.85. These are both strong correlations. But if we look at this pattern here, this would come out to something like 0. The statistics would say there's no significant effect. But there's sort of a quadratic effect, this U shape, meaning there's a peak in the data. So this is between leisure satisfaction and work satisfaction. There's a sweet spot where these two things meet. If you're completely satisfied in your work, you might not be as satisfied in your leisure. If you're completely satisfied in your leisure, you might not be satisfied at work. This is a more complex relationship, which is why we have to look at the data and visualize the data. So data visualization is super important. All of these graphs have the same correlation value. They all came out to a moderate correlation of 0.5. It's important to look at more than just statistical significance or the measure of a statistical test because sometimes there's more going on. Okay, we need to look for trends in data visually as well as statistically. So psychology is complex. It's difficult when we want to make decisions and generalizations in an accurate way. So we need to follow a few rules of thumb. We think about the limitations of generalization. We'll write about the limitations of your studies in your paper. You're going to include it in the discussion section. We have to think about the limitations placed by the sampling methods used and the limitations placed on research by statistics. So statistics helps to guide us, but they're imperfect. There are errors in our statistics, and we have to take them for what they are, right? We have to take them as suggestions, suggesting different trends, and something that needs to be tested again and again to confirm validity. All right, so I hope you enjoyed dipping into statistics and generalization and decision making. Remember that this particular topic goes together with the statistics review. So our overview of the main types of statistical tests. Make sure that you're giving that a look as well, and I will see you over in the next one. All right, bye.